How much stress can that thing take before it breaks? Stress. S-T-R-E-S-S. Stress. I think I must have learned about stress in an engineering context for the first time, maybe the second year of college, in a civil engineering class, and that was probably the first time I thought that maybe I should have been a civil engineer instead of a biomedical one, because it was really cool. I mean, I was really interested in, I remember this, I was so interested and reveled in the idea of calculating and quantifying stress. And I do not mean the psychological phenomenon of stress, although it's a cool analog. I am talking about the physical or engineering version of stress, which is when you apply a force across a unit area. When you apply force across a unit area, that sounds a lot like pressure, doesn't it? Yeah, it's got the same units as pressure. So an example of stress might be if you imagine one of those wrecking ball things, like a really, really heavy ball hanging from a cable, the one that they swing around to smash into buildings and stuff. Well, let's just imagine it's very peaceful. It's a very peaceful wrecking ball, and it's just hanging still. Heavy, heavy wrecking ball hanging from a metal cable. That cable has a diameter. You can do some math, calculate the cross-sectional area of that cable. And then we can also measure the weight of that heavy wrecking ball at the bottom. Maybe the wrecking ball weighs 200 pounds. I don't know. I don't know how heavy a wrecking ball is. And maybe the cross-sectional area of that cable is 10 square inches or something. Well, you get the stress through that cable by dividing the 200 pounds by the 10 square inches. And, well, I guess in this case, it would be 20 pounds per square inch. And that's the stress through that metal cable. And the truth is, there's a lot more complexity that can go into this, because forces may not be applied through an area perfectly perpendicularly. I mean, in my simple example, the force was straight through that cable. But hey, in real life, when you have cars driving across bridges, you've got forces from gravity going straight down onto that surface of the road. You've also got friction applying forces parallel to the road. Maybe they're going to be applying shear stress through that road. You can have combined stresses, whether they are shear or compressive or tensile, or maybe you have stresses in liquids and gases. And there's a lot of cool math and geometry and diagrams that you can get all mixed up into that calculation of stress and analysis of stress. And you can write complex computer programs to map out what the stresses look like in any 3D object. There's lots of complicated stuff you can do with stress. Why do engineers go through all that rigmarole to calculate these things? What's the point? Stress is important because everything has a breaking point. That's the interesting part, because that's where it sounds a little bit like psychological stress, right? We all have a certain level of stress we can handle in different situations before we break. Well, so does that cable. So do the columns under the bridge. So does the glass in my cup. We want to analyze stress in different materials and situations because we want to prevent failure of our materials and of our designs. If we stress out our materials too much, something's going to break, something's got to give. And as engineers, hopefully we will prevent that. Stress is our engineering word of the day. Hey, this is your host, Pius, saying thanks once again for listening to the Engineering Word of the Day podcast. If you like what I'm doing, please let me know. You can support me by donating on Patreon. My Patreon's at patreon.com/PiosLabs. Take care.